Automatically, correct.
Wow, it's great to see everyone here from everywhere.
Oh, yeah. There's this old sci-fi book, and there was this great setup where there's some funny parts in it, and they're showing off their big old supercomputer, and it's like the best thing ever. You can talk to it.
Wait a second. Stop for a second, Dave. You've got to repeat.
I do.
Oh, we did this last month too. Let me make sure it's not accidentally me.
All right, testing 1, 2. Who is it?
How's me? Is that echoing or no?
Okay, how about now? Now,
no echo.
No echo?
No echo.
No echo.
No echo.
No echo. Okay.
And it's 9.
We're good.
Mm-hmm. Thanks, everyone.
Yeah.
They're telling us.
All right. Well, okay. So apparently we're starting out with no echo, unlike last month when we had a really wonderful echo. So hello, everyone, and welcome to the July NASA Night Sky Network member webinar. We're hosting tonight's webinar from the Astronomical Society of the Pacific in San Francisco, California. We're very excited to present this evening's webinar with our guest speaker, Dr. Nikki Viall from NASA's Goddard Space Flight Center. Welcome to everyone joining us on YouTube. We're very happy to have you with us. These webinars are monthly events for members of the Night Sky Network. Information about the NASA Night Sky Network and the Astronomical Society of the Pacific. To get some more info, you can check the links in the chat. Before we introduce Nikki, here's Dave Prosper with just a couple of announcements.
Alrighty, folks. I did have a lot more tonight, but thankfully we could whittle this down a bit. So, the fun stuff. First up, just to let you know, we did our quarterly report for clubs that reported on their events for between April and June, and clubs that held events and don't yet have all toolkits will be receiving another toolkit in the next couple of weeks. Also, the following 5 clubs won a prize, a Celestron First Scope, which their events were chosen randomly from all of the reported events held between April and June this past year. And the winning clubs are the Astronomical Society of Kansas City, the Umpqua Astronomers, Astronomy Club of Asheville, the Carolina Skygazers, and the St. Louis Astronomical Society. So you will all be receiving some Celestron First Scopes in the next few weeks. We had a slight delay when ordering them, surprise, but they should be there pretty soon. And and one more thing, just a little bit. It might seem a ways off, but International Observe the Moon Night is coming up way faster than you think. The main event is scheduled for October 16th, Moon Night, and it seems like it's a long ways off, but I don't know about you all, but this year it's flying right by for me. It may be for you. So just want to let you know that if your club posts any public events in the Night Sky Network calendar between October 8th and 24th with Moon anywhere in the title, their events will be synced up with the event calendar for the International Observe the Moon Night website. And just if you don't want your event synced, just don't put Moon in the title or set the privacy to a club only event or a private. And if you schedule those events by September 1st, we'll ship your club a packet of fun Moon outreach goodies, which will be great for your International Observe the Moon Night event that you have hopefully scheduled. So, and all the info I just said, that's going to be on our newsletter in the first week of August, or you can just message us at nightskyinfo@astrosociety.org for any additional details. And that's all I got. And back to you, Brian.
All right. Thanks, Dave. For those of you on Zoom, you can find both the chat window and the Q&A window at the bottom edge of your Zoom window on your desktop. Please feel free to greet each other in the chat window or to let us know if you're having any technical difficulties. You can also send us an email at nightskyinfo@astrosociety.org. Any questions that you have for our speaker this evening, please put those in the Q&A window. So all of the questions that we'll be answering are going to be from the Q&A. And so if you put them in there, we won't lose them. They won't end up being way at the top of a big scroll in the chat. So put those in the Q&A window, and that'll help us keep track of what gets answered and what doesn't. So again, I want to welcome everyone to the July webinar of the NASA Night Sky Network. This month, we welcome Dr. Nikki Viall to our webinar. Dr. Nikki Viall is a research astrophysicist at NASA's Goddard Space Flight Center and a mission scientist for the PUNCH mission. She earned her BS in physics and astronomy from the University of Washington, go Dogs, and earned her PhD in astronomy from Boston University. She's a 2018 winner of the Karen Harvey Prize from the Solar Physics Division of the American Astronomical Society for a significant contribution to the study of the sun early in a person's professional career. She was awarded NASA's Early Career Achievement Medal for fundamental contributions to understanding coronal heating and the slow solar wind, and for valuable service to NASA, the science community, and the public. She's been a highly visible member of NASA's outreach and media team, including the August 2017 Eclipse and the Parker Solar Probe launch and first results, with over 70 live shot television interviews. And so I can't even imagine being on TV once, let alone 70 times. So please welcome Dr. Nikki Viall.
All right, thank you so much. So this is the part where I do the share screen, and we see if I remember how to do it. And then I do this.
And you need to swap screens. There you go.
All right. All right. Well, hello, everybody. I'm so excited to be here and to talk to you today about the PUNCH mission. PUNCH's polarimeter to unify the corona and heliosphere. So I'm going to be talking to you about what those words even mean and how that can connect with a lot of the projects that I know a lot of you guys are working on. So I wanted to start by acknowledging the PI of the PUNCH mission, Dr. Craig DeForest, the project scientist, Dr. Sarah Gibson, and the outreach lead, Dr. Sherilyn Morrow, who helped put this, a lot of the material in this presentation together. All right, so I'm going to start with this video here. This is just to give you a flavor of what PUNCH is. This is the launch sequence of PUNCH, a simulation of the launch sequence of PUNCH for when it's going to launch. Likely the launch vehicle will be larger than what is shown here, but this part here, after the deployment of the 4 instruments, and as they get situated in their orbit around Earth, this part is all accurate. So I'll come back later to exactly what PUNCH is doing and what PUNCH is studying, but just to give you a flavor to start with. PUNCH is going to be in low Earth orbit, and that's what this shows here. The 4 spacecraft that we have start off at the top, and then they move down in their orbit to get them just exactly aligned so that PUNCH can study the sun. Here we are with the instruments deploying on one of the WIFI instruments, the wide field imagers, and then here is the NIFI, the narrow field imager. These are just different ways that we're going to be looking at the sun. The wide field imagers, we have 3 of them. So 3 of the 4 of these WIFIs, they have to be exactly evenly spaced in their orbit around the Earth so that they can piece together these images of the material coming from the sun. So this shows the orbits, showing the instruments coming into their alignment, shows how in orbit around the Earth, the observatories align themselves just perfectly so that they can image and study exactly what it is that PUNCH is meant to study. All right, so taking a step back now, PUNCH is going to study the sun and the material that comes off the sun. What I'm showing here is a view of the sun that most of us are used to. This is a typical view of the sun, sunset over Puget Sound. The light coming from the sun that we see here is visible light. It comes from the photosphere of the sun. That's the visible surface of the sun. And now I have to give the usual disclaimer about never looking at the sun without special solar eyewear, can damage your eyes. But with NASA, we have telescopes that can look at the sun. And also, during a total solar eclipse, when the moon fully blocks out the photosphere, it is safe to look at the atmosphere of the sun. So this is an atypical view of the sun. It's not our everyday view of the sun, but it is a view of the sun that we can see from the Earth, the total solar eclipse. Total solar eclipses happen when the moon comes between the Earth and the sun and perfectly blocks out the photosphere, that very bright surface of the sun. The photosphere is 1,000,000 times brighter in the visible light than this atmosphere of the sun that we're seeing around during this total solar eclipse. So that's why it's so important to have the moon block out the photosphere for us to be able to see the solar atmosphere. So that's what we're seeing here in this series of images. There's 4 there. The second to left is called the diamond ring, and that happens when that last bit of the photosphere is peeking out from around the moon right before you go into totality. Zooming out, this is another view of a total solar eclipse, but now we've zoomed out and you can see all of the structure in the solar atmosphere. Now the light that we're seeing, this is visible light that you can see with your eye. And what happens is it's the sun's light that scatters off of electrons, free electrons in the atmosphere of the sun. That's the light that we're seeing here, the scattered light. We call that Thompson scattering. And then because the density of the atmosphere of the sun falls off rapidly because it's filling space, filling the solar system, the intensity also falls off. And you can see that the outer portions of the image, you don't see as much brightness. And in fact, during a total solar eclipse, you have to take multiple images and sum them to build up the brightness. So this density, this atmosphere of the sun, this electron density is what Punch is going to look at in a lot of detail and much, much further out, even beyond where this image is taking right here, where the signal gets very, very faint. And what I want you to notice about this image is how complex the atmosphere of the sun is. Where did all that structure come from? Well, the answer is it comes from lower down on the sun, the lower atmosphere of the sun, and I'll show you a little bit more about that later. And then where does all that structure go when it goes out into the solar system? And that's the answer, that is the question that Punch is going to answer, is where does all that structure go? How does it evolve on the way to Earth? Here I'm showing another total solar eclipse. This one was the one that took place December 14th, 2020. On the left is an image taken with the SOHO spacecraft. It's showing red, but it's same visible light, white light. On the right is a total solar eclipse picture taken from the ground at the same time. And in the bottom is a comet that was imaged at the same time with both the NASA spacecraft, the NASA ESA spacecraft, and also the total solar eclipse image, saw the same thing. So these are the kinds of details in the solar atmosphere that Punch is going to get to see because it's going to look at this white light from the sun. All right, to say a little bit more about Punch. Punch is a NASA Small Explorer mission. Basically, NASA has a whole range of different sizes of missions, from little ones to medium ones to really big ones. And Punch is one of the smaller ones. The purpose of Punch is to better understand how the mass and energy from the sun's atmosphere, which we call the corona, how all of that becomes magnetized plasma and gets expelled into the solar system. And we call that the solar wind. It has 4 small satellites. That's the mission architecture. You saw that in that opening movie. 3 of them are wide field imagers, and one of them is what we call the narrow field imager. And they take 3D imaging of the plasma from the sun as it flows out into the solar system. We use polarized light, polarized visible light, and that's how we get the third dimension, which I'll come back to later. The 4 spacecraft have synchronized operation, and they're very rapid imaging with high spatial resolution and high sensitivity. A little bit more about the science that Punch is going after. This is a artist rendition of the sun on the lower left, and then a lot of detailed structures that are being thrown off of the sun and ejected into the solar system. The purpose of Punch is really to understand all of these different dynamics coming off of the sun and how they interact with one another. And we are trying to understand everything from the global scales down to those little wrinkles that you see there and how those couple to one another. And so Punch is going to fully discern this, we call it cross scale, when we look at how those big structures interact with the little structures all together to unify the sun's atmosphere, the solar corona, with the solar system or the heliosphere. All right, so back to that first question of where does all the structure come from in the first place? And it comes from the lower atmosphere and the photosphere. Here what I'm showing is the visible surface of the sun taken in white light. It looks pretty plain. There are some little dark spots, those are sunspots, and in fact, those are locations of intense magnetic field. The other thing about the sun is that when we look at the sun in different wavelengths, it actually turns out that we are looking at different temperatures of the sun and different heights, of the solar atmosphere. So as we look in different channels and ultraviolet channels of the sun, we see a lot more structure. And actually we're looking at hotter plasma. It gets up to several million Kelvin or several million degrees, where the photosphere below it is only 6,000 Kelvin. So the atmosphere of the sun, the solar corona, is about 1,000 times hotter than the visible surface below. That's amazing because it's like if you were to walk away from a fireplace and it got 1,000 times hotter. So that's already a pretty cool thing. That's where the structure comes from. And it comes from the magnetic energy. The magnetic fields on the sun connect down through the photosphere and connect out into the hot corona. And all of that magnetic energy, the tangling and twisting of those magnetic fields have energization, and then they dissipate that energy up in the atmosphere. And that's what creates the hot corona. So here I'm showing drawn on field lines, magnetic field lines on top of the ultraviolet. We can see that that is what creates that structure. The other thing to note is that very hot material is called plasma, where the electrons and the protons are no longer bound together. And plasma can't cross magnetic field lines, so it's linked to those magnetic field lines. And in June of 2021, so just like over a month ago, the US Postal Service issued NASA Sun Science Forever stamps. And here I'm showing the images. So these are images in the ultraviolet. There is one white light image there in the lower left. The rest of these are ultraviolet images of the sun taken with Solar Dynamics Observatory, seeing these different layers of the sun, this complexity that's linked to the magnetic field. And so you too can have these stamps and mail all of your friends using these. So our goal with Punch is to take those sort of, look at that atmosphere of the sun, but look at it all the time and look at it in high definition with high resolution. This here is a composite image of of SOHO on the outside. The red is SOHO taking a picture of the solar atmosphere in white light, even though it's false colored red. In the middle is the total solar eclipse from 2017 that we could see here in the United States. And then in the middle is an ultraviolet light image taken with SDO of the lower atmosphere. So with our spacecraft, what we can do is create these artificial eclipses, artificially, without having to wait for the moon to cross in front of us. We can block out the photosphere of the light from the photosphere of the sun and look at the much, much dimmer atmosphere around the sun Now that hot corona, because it's so hot, that hot atmosphere, this 1 megakelvin atmosphere, actually expands outward and fills the solar system with plasma that we call the solar wind. So these are white light images taken with the stereo mission. It's a coronagraph on the right, and then a bigger coronagraph in the middle, and then a heliospheric imager on the left, looking at that plasma as it fades out of the view of the coronagraph and into the heliospheric imager. Notice the star field, how closer to the sun, the star field, you can't even see it hardly relative to the solar wind, but out here, the star field is really intense compared to the solar wind that we're trying to image. And it impacts all of the, let me see if I can play this again. That's Mercury right there in the field of view. And the line up and down is how it affects the detector. So that's Mercury. The solar wind affects all of the planets. It fills our solar system all the way out past Pluto. So that was it interacting with Mercury, and it also interacts with us here on Earth. Okay, so NASA Heliophysics. I'm a heliophysicist and I work in the heliophysics division at NASA. So heliophysics is the study of how the sun impacts the heliosphere, which is this bubble created by the plasma that's emitted by the sun. So this is a cartoon, not to scale, representation of the sun and the Earth. The sun is on the left, and there are the layers of the sun, some of which we talked about. There's the core at the center, the radiative zone, the convection zone, and then that solar photosphere, that visible surface of the sun, and then the atmosphere of the sun, those higher layers where it gets hotter and hotter. And then that plasma expands outwards, becoming the solar wind. On the right, we see the Earth, again, not to scale, but a cartoon representation, and the magnetic fields of the Earth. Now, since plasma can't cross magnetic fields lines, our Earth's magnetic field protects us from the plasma and the energetic particles coming from the sun. Coronal mass ejections, which are big magnetic explosions on the sun, lead to the northern and southern lights. This is a cartoon movie showing some magnetic fields rooted in the photosphere, rooted in those sunspots, those dark sunspots. And that magnetic energy, the magnetic fields build up energy and stress. And when they build up enough stress, eventually there's an explosion. And those explosions we call coronal mass ejections. They spit out chunks of magnetic field and plasma out into the solar system. This is an actual video of an actual coronal mass ejection taking off from the sun, taken with Solar Dynamics Observatory in the ultraviolet light. Okay, back to the cartoon now. So this bubble, this blob of plasma gets emitted out, going very, very fast sometimes, having a lot of energy, and then it can interact with our planets. The first planet it might interact with is Mercury. It'll be a different interaction depending on the planet because each planet has different magnetic fields and different atmosphere, and that will make the CME interact differently. The next one would be Venus. And then of course, after Venus would be Earth. Now, it's not often that the planets align like that and this coronal mass ejection hits each planet one at a time like that, but sometimes they're very large. And so a part of it will hit one planet and then a part of it can hit another planet. So here it is on the way to Earth. But again, we have Earth's magnetic field protecting us, and plasma can't cross magnetic field lines. So, but it feels a pressure from that plasma being pushed into it. So the front side of our magnetosphere gets compressed. That energy gets put into Earth's magnetic field. Earth's magnetic field gets stressed. A lot of that stress is carried on the night side and the tail. Then that stress gets released, energizes particles. Those particles interact with Earth's atmosphere and cause the aurora borealis and the northern and southern lights. The interaction of those energetic particles with the atmosphere, it's kind of like neon lights. It's the same kind of interaction. And now we're seeing actual videos of actual aurora. If you haven't seen aurora in person, The videos, even though they're amazing, really just can't do it justice. I would say a total solar eclipse and the aurora are two things that you have to see in person. It's just such an amazing experience when you actually see it. Your eye picks out things that the videos and the images just don't capture. It's definitely a visceral experience. Okay, so the sun goes through cycles. A solar cycle lasts approximately 11 years. So over the course of 11 years, the sun goes through a magnetic activity cycle where it increases in magnetic activity and has more of these coronal mass ejections and then decreases. And that's what these images show here. Starting from the top, it's showing the sun in ultraviolet taken in 1996. So this was actually a whole solar cycle ago. Anyway, there's not much structure there. And then as we go around the dial counterclockwise, we see a little bit of increase in ultraviolet, those spots of ultraviolet intensity in like 1998, 1999, it sort of picks up. And then 2001 was solar maximum. And that's when there were all these spots of intense ultraviolet activity, intense magnetic field, lots of coronal mass ejections, and then it comes back down again. And actually right now we're headed back into another solar maximum. But actually even on quiet days, even when it's solar minimum, still the sun constantly has smaller explosions as it creates the solar wind and creates this plasma that it's sending out into the solar system. And this is a series of images taken with AIA. And it's not your screen, it is jumpy because it's just the AIA images as taken, put together. But anyway, we can see all of the structure and all of these dynamics. There are some CMEs, but there's a lot of dynamics even on days when there aren't any coronal mass ejections. And many of these smaller bursts of energy create a solar wind plasma that's filled with structure and variability. This is 3 days of coronagraph data taken with the stereo spacecraft. This is a special campaign where we did deep field exposure so we could really get some of the details that we usually don't see. The solar wind, even without a coronal mass ejection, is just filled with structures. And I've pasted the Eclipse image on top there just to give you a sense of scale. The coronagraph blocks out a large portion of that lower atmosphere. And here we're really seeing that upper atmosphere as it turns into the solar wind. So Punch is going to do this at much higher, much further out all the time at this super high resolution with this super excellent sensitivity. So this is a zoom in. The solar wind is really treacherous to those of us living on Earth and who have to live in this solar wind. So the upper left is that movie I just showed. The blue square is showing the movie that I'm playing right now, the square of the movie. And then what I'm showing in that little blue dot is the whole day side of Earth's magnetic field. So that whole bubble carved out by Earth's magnetic field is just that little dot there. And notice all of these structures from the solar wind that are just the everyday solar wind totally engulf the Earth's magnetosphere. So we need to understand these, both the big structures and these smaller ones, because relative to the Earth, they're all big. And in fact, this is a simulation showing just those everyday structures. When they get to the Earth, they still compress and release the Earth's magnetosphere. It's because since the plasma can't cross Earth's magnetic field, there's an effect of pushing. It's like a forced breathing on the magnetosphere. And in fact, some of these dynamics can interact with Earth's radiation belt. That's the cartoon that I've pasted on top there with the colored donuts. A lot of our satellites have to live in Earth's radiation belt. So it's really important to understand the kind of radiation, the kind of energetic particles that are in the radiation belt, where exactly they are and what's going on there. And in fact, the aurora that we saw in the previous movie, they're happening all the time too. Their intensity gets more or less depending on these big storms, but even the aurora are happening on these quiet everyday interactions. So the point is there really are no quiet days on the sun. And that's why we need punch to help us understand both these big events and these small events. So punch again is the polarimeter to unify the corona and the heliosphere. So to unify these structures that we see lower down with the structures that are headed towards the Earth. On the left, I'm showing an image taken in white light with SOHO, with one of these artificial eclipses that we call coronagraphs. And this is one of the ways that solar physics has traditionally studied the sun, through remote imaging, for remote images in white light and ultraviolet and spectral lines, very similar to astronomy. And that's because of the history there, which is that solar physics came up through astronomy primarily. In contrast, heliospheric physics, the study of the solar wind and the coronal mass ejections right before they hit the magnetosphere, in the past, that's been primarily done through in situ. And this graph on the right is showing an in situ measurement of a coronal mass ejection. In situ just means you drop the probe at a location and you're measuring right there what the temperature, what the density, what the magnetic field is. And so you get really great, precise information, but it's just at that one point. So the solar wind and the heliosphere has traditionally been studied more in this in situ way, solar physics more in this remote way, but punch is going to take the imaging and all of those techniques that we've developed over the years and move it out into the heliosphere. So punch is not the first one to do this. Stereo did this first. We're really standing on the shoulders of giants in that sense. What I'm showing here is what stereo imaged. Stereo also had white light imagers, stereo as in two. There were two stereo spacecraft. So the little yellow circle in the very center is the sun. The red circle is one of the white light coronagraphs. The blue images are heliospheric imagers on stereo, and then the gray images on the outside are the outer heliospheric imagers. But notice it's all in along the equator, along what we call the ecliptic. Their stereo didn't image far above the poles. So there's gaps in our knowledge there. And the punch's field of views are those concentric yellow circles. It's going to take images over the poles and where stereo took images and do it at higher resolution, spatial resolution, temporal resolution with better sensitivity so that we can really fill in all of these different gaps that we've had in knowledge. And over the poles of the sun is especially interesting because sometimes we can get these quiescent, these quiet solar wind flows, but they can be really, really fast over the poles, twice as fast, in fact, than the flows coming out at the equator sometimes. Here's another view of how punch will fill in the gap. This is also from the suite of instruments that were carried on the stereo spacecraft. On the right, it's the lower corona in ultraviolet, and then there's the upper corona viewed in the coronagraph. And then there's the two heliospheric imagers. And the black spots are spots where the instrument's field of view don't overlap. And so when a coronal mass ejection, for example, as this example shows, the coronal mass ejection crosses from one instrument into the other, and you lose it for a time period. You lose it while it goes between the gap, or at least you lose part of it. Furthermore, those instruments are different. So the characteristics of the thing you're trying to measure changes across those boundaries. Is it because the instrument is different? Maybe, probably. The instruments are very different. They have different requirements, sensitivities, specifications. But also it could be different because physically the object, the coronal mass ejection or the solar wind, has changed across that boundary, because our models also predict that there are physical boundaries there, locations where the physics changes. So it could be either. Punch is going to have matched instrumentation and overlapping field of view, so we can fill in those gaps as well, so that we can fully watch from the upper corona all the way out into the heliosphere as these important transitions take place, as things advect and flow outwards. All right, so punch has two kinds of cameras. They're really kind of the same thing. We have the NIFI, the narrow field imager. This is a coronagraph where the In the middle, we block out the photosphere. Call that the occulter. The heliospheric imager looks off to the side, but it's still looking in white light. And instead of an occulter, it blocks out the photosphere with its with the solar baffles and with the solar baffle. All right. Also, I wanted to point out that Wi-Fi is using an optics that are based off of the Nagler eyepiece. So I'm sure a lot of you know Al Nagler is known to many in the amateur astronomy community for founding teleview optics and really revolutionizing the eyepieces used for amateur astronomers because of the ability for those images with the eyepiece to make very wide, but also very sharp images. And so Wi-Fi is using the same thing, very similar idea. The optics are similar to a 40-degree field of view eyepiece, but operated in reverse. The eyepiece accepts real images from the telescope and outputs parallel rays for viewing, whereas the Wi-Fi accepts parallel rays from the sky and creates real images for the CCD. As I said, the Wi-Fi optics are based on the Nagler eyepiece and built by TeleView and extremely achromatic and coma-free. All right, so back to the orbital dynamics. The 4 spacecraft, 3 of them are the wide field imagers and 1 of them is the NIFI, are in low Earth orbit, and they're sun synchronous, which means they're always pointed at the sun, and they do that by being on the dawn-dusk terminator, so they can always look at the sun. On the left is a movie showing how this orbit sweeps out a full view of the solar system, of the inner solar system, of this solar wind, these coronal mass ejections as they come off of the sun. So the NIFI field of view is in the center there, and it images the upper atmosphere really close to the sun. And then the 3 Wi-Fis each look off to the side around the Earth, and over the course of the 90-minute orbit, they sweep out that whole portion of the sky. Now, this is a huge swath of the sky. If your eye was sensitive enough to see this solar wind all the way out, this would occupy an enormous portion of the sky. It would be enormous. I said that. Okay. Now to the P in punch. P in punch is for polarized, and polarized has to do with the electromagnetic waves, the light. This is a cartoon of electromagnetic waves. The middle one is linearly polarized light, where the E field and the B field are oscillating in a plane. The type of scattering that happens on the sun off of the free electrons in the solar system, in the solar atmosphere, is called Thompson scattering. And it makes a certain portion of linearly polarized light. And the amount of linearly polarized light has to do with where you, the observer, are, punch, where the sun is, and where the plasma is that you're measuring. And so that angle determines how much linearly polarized light you'll receive. And so by measuring that amount, you can actually localize in 3D space how close or far away the structure is from punch. Punch is also extremely synergistic with a lot of missions that are going to be up. Parker Solar Probe is one. Parker Solar Probe was launched in August of 2018. Parker Solar Probe does the opposite of punch. Punch brings imaging out into the heliosphere. Parker Solar Probe brings in situ measurements closer to the sun, into the upper corona of the sun. So this is a launch sequence showing the orbit of Parker Solar Probe. It uses gravity assist around Venus to get in close to the sun. And in fact, it gets down to 9.86 solar radii. So that is about 4 million miles. So for context, Mercury is on average about 35 million miles away from the sun. So Parker Solar Probe gets 10 times closer than Mercury's orbit. For context, prior to Parker, the two Helios missions were the closest that we had ever been measuring the solar wind, because they went out to Mercury's orbit. And Solar Orbiter is also going to be about at that Mercury orbit type of distance. So Parker Solar Probe is actually named after Eugene Parker, who predicted that that mega Kelvin corona, that really, really hot corona, ought to be expanding outward and making a solar wind. So the picture on the left is of Eugene Parker right after he wrote that seminal paper predicting the solar wind. And the picture on the right is of him at the launch of Parker Solar Probe. And this is the first time a mission has actually been named after a person who is still alive. So that's pretty cool that he got to see it launched. Parker Solar Probe also has an imager, a white light imager. It's called WISPER. So this is one of the pictures that WISPER took of the comet Neowise, seen on July 5th, 2020. The lower tail is the comet's dust tail, and the thinner upper tail is the comet's ion tail. So actually, comets were the original solar probe, if you will. Biermann saw that ion tail and saw that it looked different than the dust tail and predicted that there ought to be flow coming from the sun to make that ion tail. And in fact, he was correct. So the dust tail is actually caused by solar, it's caused by radiation pressure, but the ion tail is actually caused by these, this plasma from the sun, the solar wind, interacting with the comet. So back to how PUNCH is synergistic with the other missions. Here's an example of stereo actually taking images of the outer corona in white light. And we can see Parker Solar Probe, there it goes. That's where Parker Solar Probe flew through the upper corona of the sun. And so PUNCH is going to do the same kind of thing, be imaging in high definition at very high resolution with high sensitivity as other spacecrafts fly through what we're seeing. It's synergistic actually with a lot of different missions that are going to be flying. What I'm showing here is a simulation. The sun is in the center there, it's rotating. The sun rotates every 28 days. And so it emits the solar wind directly outwards, straight outwards. But like a sprinkler, it's rotating underneath. And so this creates the Archimedean spiral shape here illustrated in purple. Those are the magnetic field lines in that spiral shape that the magnetic field lines take. Also, there are different orbits of the planets shown around here and Earth. And of course, PUNCH will be in orbit around Earth. So PUNCH will be imaging from Earth. And then some other imagers like stereo, solar orbiter, Parker Solar Probe, and how each of these missions will be looking at the solar wind and the solar corona from different viewpoints, or they'll be flying through while somebody else is imaging that plasma. And by piecing together these different viewpoints, we can understand a lot better how the corona and the solar wind and all of its structures evolve and are created. And so PUNCH is going to be a really important part of all of this. Here I'm showing the movie on the left is imagining we're looking down from the pole of the sun, and we see what's called the co-rotating interaction region. I'm going to see if I can play this again. Let's see. Oh, maybe I don't want to play once. Oh, well, okay, this still is good. Okay, so this is a co-rotating interaction region. This is a simulation as though we're looking down on the sun is the leftmost panel. And then the right two panels are what PUNCH will see. So PUNCH is going to image these co-rotating interaction regions. So what happens is when this solar wind is emitted outwards, sometimes it's fast and sometimes it's slower. In fact, the speed difference can be up to a factor of 2. The solar wind goes straight outwards, but then the sun is rotating underneath it. So if the sun spits out a slow speed wind and then rotates and underneath it spits out a fast wind, then that creates a compression front as the fast wind plows into the slow wind. And in fact, if this continues for a while, we get this Archimedean spiral shape again in this front of compression as the fast wind is plowing into the slow wind. And that's what this movie is showing. That's what the green spiral shapes are, these locations where the density has plowed up. And in fact, it can plow up so much that a shock is created. And these shocks, and even just the compression regions before the shocks, can also be really important for the interaction with Earth's magnetosphere and energization. All right, next I wanted to talk a little bit about the outreach that Punch has set up. So on our Punch website, we have these science objectives that are written in sciencey jargon that are super specific to the way heliophysicists talk about the sun and the solar wind. But there's also a mirror of background information, a mirror website that has the same idea, but it's really getting rid of the jargon and just talking about the basic science behind these very specific targets that Punch is after. So I've got the web page there listed on the bottom. But the idea is, instead of what are the shock dynamics and 3D and morphology, it's just then the outreach site is really just what is a shock and how does that look in the solar system. Another aspect that's really cool about the outreach program that Punch has is that it's focused on ancient and modern sun watching. That's the big theme of the Punch outreach team. And the three images here I've got on this panel, the lower left is an ancestral Puebloan petroglyph from Chaco Canyon. And in 1097, there was a total solar eclipse. And they believe that this petroglyph could have been a petroglyph of that total solar eclipse, which would have been the first recording that we know of a total solar eclipse. The one we usually think of is the one in the middle, which is an 1860 drawing of a total solar eclipse from Spain. And it's thought that that distortion in the lower right is from a coronal mass ejection. And then for context, on the right is the 2005 coronagraph image from NASA SOHO with a CME as it's progressing. So you can see the similarities there. So again, the idea with the outreach is that it's a link between ancient and modern sun watching theme. On the upper row there, I'm listing Punch, the Punch mission, and Parker Solar Probe, which I talked about how we're synergistic with Parker Solar Probe and Solar Orbiter. Similarly, is looking at the sun and has in situ instrumentation. So this is the modern way that we can look at the sun. But on the bottom is personal sun watching. Of course, we can watch the eclipses and so forth from the Earth. And then in the middle is the ancient sun watching in Chaco culture. And on the left, you can see the cool blending of that petroglyph on the upper left with image of in white light of the total solar eclipse. And in fact, as part of the outreach plan, they are planning to reach out to the Girl Scouts. This is the proposed patch for the Girl Scout patch that will be hopefully coming online. I know we're excited about that here. My daughter wants to do Girl Scouts, and so we're hoping to be involved in this. And then lastly, you too can see a total solar eclipse. If you haven't seen one yet, like I said, I highly encourage it. It's really an amazing experience. And the total solar eclipse of 2024, April 8th, is one that will come across a large portion of the United States. In the dark blue, that's showing the path of totality. That is to say, when the moon totally blocks out the photosphere of the sun and you can see the atmosphere around it. So the path of totality comes up through Texas and then goes up through the United States and then goes out through Maine. Those grids outlined in the sort of cyan color there, those are places where you can see a partial eclipse. So the moon won't totally block out the photosphere of the sun, but you can see the partial eclipse from those locations. So the whole continental United States will see some part of an eclipse. So that's pretty cool. So learn more. Punch has some outreach sites. We have our main Punch outreach site, but as I said, we have this mirror site with some of the jargon removed. NASA has lots of citizen science opportunities related to heliophysics. Two related to what I talked about today are Aurorasaurus, which is aurora observing, and then sun grazer. So those sun grazing comets found in NASA mission data. And then some websites that you might be familiar with, but that are related to this topic that we talked about, are some of your night sky network, the Magnetic Sun Toolkit, and the Girls at the Telescope. So that's really what I have to say. Punch is a super exciting mission. We're so excited. The Punch science goal is to fully discern the physical processes that unify the sun and its atmosphere with the heliosphere or the rest of the inner solar system. Thank you. I'll take questions.
All right. Well, thank you very much, Nikki. That's really interesting. We've got and we have a lot of really good questions here too, and I'm sure that a few more will come in as we think about these. And so let's get right to them. So I'm going to combine a few of these. And so Sherwood asks a couple questions about the time scale of a couple of the videos that you had. He noted that both the CME sequence and the auroras, he was wondering, do they really move as quickly as what you showed?
Well, probably not, because those were movies. But so coronal mass ejections can move a few hundred kilometers per second. So they can move slowly. They can move just the normal speed of the solar wind. And it takes at those speeds about 4 days to get from the sun all the way to there. So 4 days is a pretty long time. But the really energetic ones can come a lot faster than that, 4 or 5 times faster than that. The really, really fast ones can even arrive in about a day. So those are the ones that we want to make sure we capture, and we can tell whether they're coming towards us, and Punch can do that.
All right. So I'm not sure, Vasuki asked, why is the solar cycle 11 years?
Yes, I don't know. There are a lot of people working on that. We don't have an answer. It's one of the big questions. The answer has to do with the dynamo rooted in the sun's core and in the center of the sun, the magnetic field and how it gets spun up and then how it flips and in the convection zone. But the answer is we don't know. And there's a lot of people trying to understand the magnetic field. Part of the problem is that magnetic field, where all that action is happening, is below the surface of the sun. So we have to use other techniques like helioseismology to understand it.
All right, so Blaine asked, does the plasma that creates the aurora actually touch the surface of the Earth?
That's a really good question. No, it's making that light because those electrons are interacting with the Earth's atmosphere, very relative to us here on the surface. It's very high up. And so no, those in a very super duper energetic events, some of the electrons and protons that interact with the atmosphere create other energetic particles, secondaries and tertiaries. Those sometimes in a really energetic event can reach the ground, but it's very rare. It takes a really big event for that to happen. So most of the energetic particles get stopped by our atmosphere.
All right, and then kind of related to that, Joe asked, how much of the Earth's orbit is affected by the solar wind?
The orbit is not affected by the solar wind. It interacts with our magnetic field, but it doesn't affect our orbital dynamics.
So I guess there might be a couple of different ways of interpreting that. Is the solar wind, does it go out in all directions in contact, or does it actually influence the Earth's motion within the orbit? And so I suppose we could interpret that a couple of different ways. So
yeah, the solar wind goes basically straight outwards in all directions. The sun emits in all directions. up and down over the poles, out. And so it hits whatever's there, whether it's Earth or Mercury or Venus or some of the outer planets. It hits what's ever there, but it doesn't affect our orbit, but it will hit us in our orbit.
Okay, going back to the 11-year solar cycle, Lewis asks, is the 11-year solar cycle a regular repeating cycle with little variance from cycle to cycle, or has the cycle varied in length by a few years?
Yes, that is a great question. The solar cycle, I had a little tilde in front there because it is not precisely 11 years. Sometimes it's a little bit shorter, sometimes it's a little bit longer, sometimes it's more intense, sometimes it's less intense and when it reaches those peaks. That is all part of the solar dynamo studies that are going on right now, is how come some of them are a little bit longer or a little bit shorter, and trying to understand that as an active field of research.
Okay, William asks, would a huge coronal mass ejection ever simply overcome Earth's magnetic field, and what would happen if it did?
They have run simulations of that. We have really excellent simulations that can predict how much energy would it take, how much plasma, how dense would that plasma have to be, how much magnetic field would there have to be to totally overwhelm Earth's magnetic field. And so, of course, there is a limit, but all of the coronal mass ejections that we have now, they're things that we have to worry about for our spacecraft, for our astronauts. They do things, they can drive induced currents here on the Earth. That's actually a really big effect. There was an event called the Carrington event in the 1800s. It's a big solar flare, a big coronal mass ejections that drove dynamics in Earth's magnetosphere that were so intense that the ground-induced currents were so intense that telegraphs caught on fire. But it still didn't totally overtake the magnetosphere. We still had our magnetosphere, and it's still the Earth's atmosphere protected us. But certainly for our satellites, for our cell phones, for things that are wired, it's important to understand when those storms are headed our way.
And actually that kind of leads into the next question that I was going to ask. Philip asked, will this mission help us to prepare for things like the Carrington event?
Definitely monitoring will be able to tell when coronal mass ejections are headed towards the Earth. So we're not predictive. NASA does not do space weather predictions per se for space weather. That's what NOAA does, but we certainly help understand coronal mass ejections and why they deflect one way versus the other. And when they get to the Earth, what kind of structure they have, because it's both the overall structure, but also some of the substructure within the coronal mass ejection determines how it actually ultimately impacts the Earth and the magnetic field. So Punch is going to understand all of that physics of the processing and route as it heads towards the Earth.
Right, and Darian asked a question. This is an interesting one. How much of global warming can be attributed to our sun versus fossil fuels? Are there changes in the sun that Punch can analyze to help us understand the role that our sun plays in global warming?
Yeah, the short answer is the sun plays no role in global warming compared to fossil fuel. The irradiance changes with the solar cycle, but it's mostly carried in ultraviolet and X-ray. The actual irradiance changes by, I think it's like 0.01%. It's very, very small, not anywhere near to the amount to explain global warming.
Let's see. I think we have time for a couple of more here. So Stuart asked, do the solar magnetic fields reverse north-south like they do on Earth?
Yes, I didn't mention that, but yes, it's actually a 22-year cycle because the magnetic activity increases and decreases and then flips. And then in the other state, it does it again. And so that's actually part of these dynamo theories that people are trying to work out is how does the previous cycle, how does that connect to the next one? Because really it's this longer 22-year cycle. Yeah, that's a really good question.
Okay, so I'm going to go for two more here. I'll apologize up front for the people that were not getting to all of your questions. So Blaine asks, it seems that sunspots appear at certain latitudes of the solar surface. Is that accurate? If so, do we know why?
Yes, this is also related to the solar dynamo, we think. Because it's all part of the magnetic field, and what causes those magnetic fields to poke up through the photosphere and come out into the corona and make those sunspots. That does happen at particular latitudes. And then as it flips, as the solar cycle flips to the next polarity, then the whole thing starts over again. If you want to look them up, they're called butterfly diagrams because of that latitudinal pattern that those sunspots take.
All right, and last question. Lori says, I'm part of Girl Scout Stars. Any timeline on the new badge?
I don't know. Sherilyn Morrow is our outreach lead, and I know she's been hard at work on that. So I'm just excited to be on the receiving end of that, but I don't know all the details of how that's coming together just yet.
All right. Well, if you could go ahead and stop sharing. Great. So let me bring this back up. So I just want to say, that bringing these webinars to everyone is truly a team effort, including one of our other panelists this evening. Over the years, Carolyn Ng, an education specialist in the Heliophysics division at Goddard Space Flight Center, has introduced us to a great many solar scientists who we have featured in these webinars. And so thank you, Carolyn, who's with us tonight, for all you have done to help us bring the very best of NASA science to the Night Sky Network. So thank you so much.
You're welcome. Thank you, Nikki and Brian and Vivian and Dave.
So, and thank you, Nikki, for joining us this evening. And thank you everyone for tuning in. You'll be able to find this webinar along with many others on the Night Sky Network website in the Outreach Resources section. Each webinar's page also features some additional resources and activities. We'll make sure that this is up on that site. And it is also on the YouTube, the NASA Night Sky Network YouTube channel. And we've been live streaming, and it automatically records to that. Join us for our next webinar on Wednesday, August 18th, when we bring you an update on the Lucy mission to study the Trojan asteroids at Jupiter with Dr. Kathy Alkin. So we're kind of going from looking inward in the solar system to looking back outward. So keep looking up, and we will see you next month. And so good night, everyone.
Good night. Thank you, Dr. Viall.
Thank you.